In this week's presentation, we want to talk about diagnostics and remedial measures associated with our simple linear regression model. My intent is to give you a bit of an overview for the material covered in sections 3.1 through 3.3 and 3.8 and 3.9. Naturally, this presentation is not a substitute for reading those sections, so my expectation, and of course my recommendation, is that you read them over carefully. The essence of what we intend to do in Chapter 3 is to investigate the assumptions regarding the random error terms in our model, that is, the epsilon sub I. We have assumed that those random error terms are independent, normally distributed random variables with a mean of 0 and a constant variance of sigma squared. And of course, we have no way of knowing what those random error terms are, because in general we are looking at data sets and we don't have the entire population to which we want to apply our models. So the epsilon sub I are beyond our reach. But naturally, the residuals, the E sub I, are reasonable placeholders for those epsilon sub I. We might be able to investigate the behavior of the residuals in order to get some sense of the validity of the assumptions regarding the random error terms. Some of the purposes that we might want to apply the residual analysis to are the assumptions of linearity, the assumption of constant variance, etc. And we're certainly going to discuss those kinds of things in great detail in the Math 431 course. But I do want you to have some understanding of how we can use the residuals to assess the validity of those assumptions now. Of course, one of the very first assumptions we make about the relationship between our predictor variable and our response variable is that that relationship is linear. And our residuals can help us assess that. Now I have a worksheet, an Excel worksheet called windmillanalysis.xlsx, and I'm going to go to it now. And of course it'll be posted for you to take a look at. But what I have here is I have some data associated with DC output as a function of wind velocity for 25 observations, windmills. And if you take a look at a scatter plot associated with those data, you see that as the wind velocity increases, the DC output increases. And we might consider modeling that behavior using a simple linear regression model. And in fact, I went ahead and ran using Excel the simple linear regression procedure. And if you take a look at the p-value associated with that model, you see that it's quite low, and so and the R-square value is reasonably high, 0.8745. And so we might be tempted to think that this model is legitimate. But my concern is generated by taking a look at the plot of the residuals versus the fitted value of the DC output. Now we could just as easily plotted the residuals versus the predictor variable and got the same thing, because we're dealing with a simple model here. And you notice that when you look at the residual plot, there's a pattern. At one point the residuals are negative, then the residuals are all positive, and then they become negative again. And so this is evidence to suggest that we might want to consider whether or not the assumption of linearity is legitimate or not. And in fact, when I first look at this pattern, I would be tempted to model the behavior between DC output and wind velocity using a quadratic model. But the thing about quadratic models is, they go up and then they come back down again. And if we take a look at that scatter plot, You notice that as the wind velocity increases, it looks like the DC output is approaching an asymptotic condition. And so what I did, and it's highlighted here in this yellow text box, is I am going to use a model where I'm going to investigate the relationship between the DC output and the reciprocal of the wind velocity. So I'm going to take 1 over the wind velocity. I'm going to transform my predictor variable, and instead of using wind velocity, I'm going to use 1 over wind velocity. And when I look at a scatter plot of DC output versus wind velocity, you notice that that certainly looks like it might be modeled reasonably well using a straight line. And in fact, here's the worksheet where I've transformed the data. That's easy enough to do. Just take the reciprocal, and then I ran a simple linear regression of DC output versus 1 over the wind velocity, and notice the p-value, notice the r-square value associated with that model. And this model is awesome. So clearly there's a statistically significant relationship between 1 over wind velocity and DC output. And when I look at the residuals associated with that modified model, they don't show any discernible pattern. And so I would be tempted in this particular case to use that transformation. Now, section 3.8 or 3.9, it talks about transformations. I think it's 3.9. At any rate, I would urge you to read over that section in our textbook. There are different kinds of transformations that one can use. Here I'm just showing the repeat of what you've already seen. The residual plot in the original model had a pattern to it that concerned me, so I did the transformation. Some discussion of what transformations might be useful. It's given in section 3.9 of our textbook, so you want to take a look at them. When I ran the regression model using a transformed predictor variable 1 over wind velocity, it was just great. And the residual plot doesn't give me any reason for concern. So take a look at this notion of transformations. It's very important. We're going to talk more about that in the Math 431 follow-up course, but clearly transformations can be useful, and are in this case. Now, another assumption that we make is the assumption of constant variance, that these random error terms, the epsilon sub I, have constant variance across all levels of x. And again, we can't investigate the epsilon sub I. We don't have the entire population, but we can certainly investigate the residuals. We could look at different kinds of residuals. We could look at the residuals themselves, which is what we're going to focus on. There are other residuals. There are standardized residuals. Some people call them semi-studentized residuals. That's where we take the residuals and divide by the square root of the mean squared error, which is an estimate of sigma, which is the notion of standardizing by dividing by the standard deviation of a quantity. Or we could look at what's called the studentized residuals. The studentized residuals are in fact the residuals divided by their honest to goodness standard deviation, indicated here as SE sub I. Now that's a difficult computation. We will again see that more thoroughly and talk about it in more detail in the Math 431 course. Well, at any rate, if the assumption of homoscedasticity is valid, we would expect then to see the spread of the residuals to be pretty much the same across all levels of x. Now, to illustrate a situation where that is not the case, I'm going to use some data which actually comes from the textbook, where we have a data set dealing with the relationship between alpha particle counts and plutonium activity associated with some standards that we know the activity level to be. And this is discussed somewhere in chapter 3, I believe, in our textbook. So you may see this data there. I have it in a worksheet, so we'll take a look at that. And that data is in a worksheet called plutoniumanalysis.xlsx. And when we look at that data, I have 24 observations. One of the observations has been eliminated because it seems that the experimental conditions associated with that particular observation were fouled, and so there seems to be a legitimate reason for eliminating it. The other thing I want to point out to you here, the reason I say that is because of the plutonium activity level of 0, the alpha count was 0.106, which is much different than what you would see for the other 0 values for the plutonium activity. So that caused some concern, and ultimately it was decided that that particular observation was fouled, and so it was removed from the analysis that I did here. At any rate, you see that there's noise in this process, and one of the things we might want to do is run a regression to see if we can't model the behavior that would allow us to predict the alpha count for this particular device given various levels of plutonium activity. And when I ran that simple linear regression model, notice that the p-value is great, very small. The R-square value very high, and so based on this, one might conclude that the simple linear regression model is just great. But there's more to the story, and if you look at an analysis of the residuals and you plot the residuals versus the plutonium activity, notice what you get. At the various levels of activity, as they increase, the spread of these residuals is also increasing. And so there's a concern about this assumption of homoscedasticity, and we need to take care of that. So here's a repeat of the picture of the graph you saw, and you notice that we have this little funnel shape, and clearly the assumption of equality of variance across all levels of x associated with our random error terms seems to be violated here, and so we have to do something about that. And there are procedures to handle that. This notion of transforming is a good approach, and it works, often. So I would ask you to take a look at section 3.9. There's a good discussion of transformations and the impact that various transformations will have given the various ways that the response and predictor variable are behaving within the data set that we have available to us. Now, one of the things I do want to mention to you is that it's sometimes the case that when we do a transformation to take care of one issue, then that transformation might present another issue. And in fact, in this particular data set, if we take a square root transformation, which is a transformation that would clearly minimize or reduce rather the variance at higher levels of plutonium activity, because the square root of 100, for example, is 10, and the square root of 10 is 3, and 3 and 10 are a lot closer than 10 and 100. So a square root transformation is a good one to stabilize variance. But in this particular case, if you do that and you look at the relationship between the square root of the alpha count and the plutonium activity, then it turns out that it's no longer linear. Now, you don't have to do that. I'm just telling you that to make you aware that transformations to take care of one issue sometimes introduce other problems. Now, one of the other assumptions we make about our random error terms is that they are independent. Remember, we have independent, normal, random variables with a mean of 0 and constant variance sigma squared. That's the assumption that we make about the random error term. And now we want to talk about, how do we assess this assumption of independence? Well, one way that you might do this is to look at a time series plot. Take a look at how the residuals shake out over time and see if there's a pattern in that plot. And if there is, then that's evidence that we have, some correlation perhaps between the error terms, and we would have to do something about that. I mean, we'd have to, try to fix that in some way. And we'll talk more about that in the follow-on course, Linear Regression 2, Math 431. Now, the assumption of normality. This gets most of the ink in most textbooks, and it is important. It turns out, however, that departures from the assumption of normality are not always, debilitating. But clearly, the F-test, the T-test, the confidence intervals, the way we build confidence intervals and prediction intervals, all of that was predicated on the notion that these random error terms are normally distributed. So clearly, if those random error terms are not normally distributed, then these things could be problematic. And so there are lots of ways that we could assess whether or not the random error terms, the epsilon sub I, are normally distributed. And all of them come back to looking at the residuals. We could just produce a histogram of the residuals. We could produce a stem and leaf display, a box plot, a graph, and see if that graph looks normal. And if it does, then we're probably comfortable with the assumption that our random error terms are normally distributed. If it doesn't, then we probably need to do some further investigation. We could employ the empirical rule. We know that if a random quantity is normally distributed, then about 68% of those observations should be within plus or minus 1 standard deviation of the mean. And so we could see whether our residuals actually exhibit that kind of behavior. We could do some statistical tests. Now, there is a thing called a chi-square goodness of fit test. It is not discussed in this context of testing the assumption of normality in a simple linear regression model in our textbook, but it certainly could be used, and maybe you've seen chi-square goodness of fit test in a statistics course that you may have taken prior to Math 325. We could produce a normal probability plot. Now, there are lots of ways to build normal probability plots. I'll show you the one that I like, and coincidentally, it's the one that's discussed in our textbook, so I expect that that's the one that you will use if I ask you to produce a normal probability plot. There are correlation tests. What we could do is we could take a look at our observed residuals and compare them to what the residuals would look like if, in fact, they came from a normal distribution. And if that correlation's high, then we would feel comfortable with the assumption of normality. If that correlation is low, then we might have some suspicions about that assumption and need to do some further investigation. Bottom line is there's lots of ways to deal with assessing whether the random error terms are normally distributed, and I would invite you, to consider all of them. A histogram. Here's a histogram of the residuals associated with the payment versus debt simple linear regression model that we've looked at previously. And so I just built this histogram using Excel, or I actually forget what software I used, but I suspect it was Excel. And that histogram of those residuals looks pretty normal. And so in that particular case, I would feel pretty comfortable about the validity of that assumption. Chi-square goodness of fit test, again, I mentioned this is not covered in our textbook. It is, as I like to say, nice to know information at this point. We may visit this in more detail in the Math 431 course. I'm not sure at this point, but I do have an Excel workbook that has a chi-square goodness of fit test in it, so I'm just going to sort of rip through it pretty quickly just to alert you to the fact that that can be done. The essence of conducting a chi-square goodness of fit test is really quite simple. We take a look at what we observe versus what we would expect to observe, and we sort of standardize it in a way, in a way in this particular case that allows us to know the distribution of the resulting quantity. And if the observed values of our residuals are close to what we would expect given the assumption of normality, then we would suspect that this chi-square value here would be small. If chi-square is small, then we would tend to accept the assumption of normality. If chi-square was large, on the other hand, we would tend to reject that claim. And again, I don't think it's critical at this point that you know how to do this. I'm certainly not going to ask you to because it's not discussed in our book, but I do have an example. It's in the payment data where I run through this. And you can take a look at this worksheet called chi-square test in the payment data SLR residual analysis workbook, and you can read about it. And you can see what I've done here is, I've broken this up into a frequency chart, and I've looked at the actual number of observations versus what we would expect if in fact those observations, those residuals came from a normal distribution. I computed the distance, that is, I computed the difference between the observed and the expected values, squared them, standardized them in a way by dividing by the expected value, and summed them up to get a chi-square value. And in this particular case, you can read through the particulars, but I just wanted to alert you at this point to the fact that there is this ability to actually do a statistical test of hypothesis to assess the assumption of normality. Now, most textbooks, ours being no exception, spend a lot of time talking about normal probability plots. Now, there are lots of ways to construct normal probability plots. All of them, in some way or another, take a look at the actual observed values of our residuals and compare them to what we would expect given the assumption of normality. Now, the expected value of the kth ordered, that is, if we took them from smallest to largest and ordered them, the expected value of the kth ordered residual when we're sampling from a normal distribution with a mean of 0 and a variance of sigma squared, which is the assumption we've made about our random error terms, is a very difficult computation. That is, the expected value of the kth ordered residual is what you see on this slide, where phi is the CDF of the standard normal distribution. And no one wants to do this integration. At least I don't. And there are a number of approximations that have been generated. Here's one. To find the approximate value of the expected value of the kth ordered residual from a normal 0-1 population, and Excel actually uses this one to generate its normal probability plots. I'm telling you straight away, I'm not a fan of the normal probability plot that Excel produces, but it's certainly legitimate, and this is the approach that it uses to generate its plot, not the one that our textbook uses. Our textbook actually uses this particular approach, Bloom's approach, to find the an approximation for the value of the kth ordered statistic. And so what we need to do in this case is we need to compute k minus 3/8 divided by n plus a quarter, find the value associated with the inverse CDF, and multiply it by the square root, the inverse CDF associated with the standard normal distribution, and then multiply that by the square root of the mean squared error to find this estimate. And then we could plot the, I said estimate, I meant expected value. We could plot the expected value of the kth ordered statistic against the actual and see if they lie on a straight line. And if they do, then that would be evidence to suggest that we do in fact have a normal distribution. So what I have here on the worksheet called GPA Exam SLR Residuals Analysis, that's a mouthful, is a small little data set where the exam is an admissions exam score and the GPA is the GPA at the end of the freshman year for a sample of 20 individuals. And so we gave them an admissions test, and then at the end of their freshman year we looked at their GPA, and the concern was, is there a relationship between the admission score and the GPA? And in order to assess that, build a little regression model using that data set, and it looks pretty good. The p-value associated with that simple linear regression model is pretty small, and one would be tempted to suggest that we have a legitimate linear relationship between the GPA at the end of freshman year and these admissions test scores, which would give the admissions office, something to think about when they're, admitting people. They can give them the test. If they do well on the test, then we would expect their grade point average to be high. Well, associated with that simple linear regression model, of course, are the residuals. You can get them outputted, straight away from Excel. And I ordered those residuals, and then using Bloom's approach, I also computed the expected value of the kth ordered residual, and then I plotted them. Oh, by the way, before I show you that plot, here's the plot that Excel gives you. And it's usually sort of scrunched up and a little hard to look at, but clearly, it looks like those values lie on a straight line, and that's the key. Like I said, though, I prefer Bloom's approach, and there it is, and it looks great. So, given that normal probability plot, I feel pretty comfortable that the assumption of normality is appropriate. Now I need to get back to the slides. Here we go. And so here's a repeat of the normal probability plot using the technique discussed in our book. And, I feel pretty good about it. The other thing that we could do is we could actually do a correlation test. We could take a look at our residuals and see what the correlation of those residuals versus the expected value under the assumption or normality would be. And if that correlation is high, then that's evidence that the assumption or normality is legitimate. If that correlation is not so high, then we might question that assumption. And I actually computed that correlation. I don't know if you saw it earlier, but here it is. So here are my expected residuals under the assumption or normality. Here are the ones that I observed and ordered, of course. And then I run a correlation using the CORREL function in Excel, and take a look at that. I mean, it's 0.988, which is very, very high. So again, I feel pretty confident that in this particular case, our random error terms are normally distributed. Outliers. Just a couple of brief comments about outliers. What are they? Well, they're extreme observations. But outliers, simply can't be discarded just because they're unusual. They happened. The only way I would feel 100% confident about discarding an extreme observation is if I had some evidence to suggest that that observation was, fouled, that there was something wrong with it, that it was not legitimate. And in that case, I would toss it. And we saw an example of that when we were looking at that plutonium activity data. That particular data point just seemed odd. Further investigation, and that's the key, further investigation revealed that it was fouled. And so, I felt okay about eliminating it. But they cannot be eliminated willy-nilly. We are going to talk a great deal about outliers and influential points. Now, it turns out that just because an observation is an outlier doesn't necessarily mean that it exerts a lot of influence in the model building process. And the best way to find out whether a particular data point is influential is to take it out and run the model and see if the model changes dramatically with that particular data point being excluded. And if it does, then that's what we call an influential point. And we are going to talk a lot, and I mean a lot, about that when we talk about Chapter 10 of our textbook in the Math 431 course. Well, the conclusion. This week is the same as every week. I've tried to give you a little bit of an appetizer as to what's contained in the reading for this week, but it's absolutely critical that you do the reading, that you do the homework, that you ask your questions, and that you understand the material in sections 3.1 through 3.3 and 3.8 and 3.9, because this is, part of the building process, and you want to make sure that you understand everything contained in those sections as you make your way through our course.